So yeah, hello. My name is Hannes Voigt, and I talk about the language task force in LDBC, the graph query language task force. As Larry was already pointing out, it's a group of people from industry and academia, led by Marcelo Arenas, and the aim of the task force is to, first of all, study graph query languages, to better understand them, and specifically graph query languages for the property graph model. And the more long-term goal is to come up with a proposal for a graph query language that can then be worked towards a standard. And what's the motivation for that? While working on the benchmarks in the other task forces, LDBC saw that there is a zoo of languages available and implemented in different systems, which makes it really hard to define benchmarks. And particularly, it also makes it hard for applications to switch between different graph data management systems, which hinders competition. And this is exactly what LDBC wants to foster, to have competition between graph data management systems. And one crucial ingredient, besides benchmarks, is that these systems have a common interface, and that is, first of all, a common query language. So that's why LDBC is investing into getting a standard query language for graph data management systems, particularly for the ones supporting the property graph model. Because for RDF, as we all know, there is already a standard. And the overall goal, as for whole LDBC, is to foster performance competition and thereby improving the systems in the end. Another aim is that we want to have, or another motivation is that we want to have closed graph query languages, as SQL is a closed language. So what does that mean? It means that the query language operates on a single data model. And for SQL, that's given if you express SQL queries on tables, and what you get out are also tables. And the nice thing about that is that by that your query language becomes composable. So you can run a query, and on the result, because it's in the same data model, you can run another query, and so on. And this is really nice. So we want that. That is heaven in terms of query languages. If we look at existing graph query languages, the picture is different. So they operate on graphs as we want, but more or less all of them use a table as a result, not a graph. So they are not closed. And so the question is, if you want to run another query on that result, if you want to be composable, how do you do that? It's not clear. So such query languages are not composable, and in terms of power of query languages, that is not nice, or so to say, it's hell. So there's another motivation why we look into that topic. I want to find out how really composable graph query languages look like, what are the principles, the concepts we need to accomplish that. To explain a little bit more why composable query languages are important and become more and more important, is the following observation. When we look how base data is structured today, so which semantic concepts are used to describe and structure the data which is actually stored in the database, then we see, particular now in the big data era, that these concepts are very fine granular, of low abstraction, And if we contrast that with what the user, so the person or the program that runs a query, what concepts we have at this end, at the user end of the database system, then these concepts are typically way more abstract. For instance, if we look at something like Twitter data, then in our database we probably have Twitter messages, retweet relationships, these kind of things. But what people are interested in who use this data are communities, topics, discussion threads, etc. So there's an abstraction in between, and probably also multiple abstractions on top of each other. And the main mean to cross these concept chasm, so these level of abstractions, is your query language. And particularly if you have multiple of these abstraction steps, you need a query language that cannot bridge just one abstraction steps, but do this multiple times, and then your query language must be composable. So this is a thing which becomes more and more important. Is there a question? Yeah.
Sometimes I've heard that people refer to this as hypergraphs, because when we talk to some customers in the intelligence side of the government, they mention this is hypergraphs. Maybe we should look at hypergraphs and see how they relate to this, where it's basically different overlays. I don't know how the concept of hypergraph relates to these levels you're talking about. Maybe
Okay, but yeah, so that is hypergraphs in terms. I mean, hypergraph is a
graph between graphs, which is related to this, obviously. I'm not sure what the relationship is.
yeah, okay, but then you would need a query language that runs on hypergraphs and produces hypergraphs still, right?
Okay. Depends on how you treat your hypergraphs, right?
Yeah. Okay, so we just take this more as a motivation for having a composable query language. That's the point of this slide. Okay, to sum up the goals of the task force, so we look for a query language for property graphs by the power roughly comparable to what SQL 92 can do. It should be composable, and to have a good language design, the concepts which made up the language should be at most as possible orthogonal. And another high-level goal is that we have a proper support for paths. So we want to have paths as first-class citizen in that query language. So where are we now at the moment? What do we have accomplished? One thing is that we came up with a catalog of functionalities. So we basically just started listing what are the functionalities we want to see covered by the query language. And this, I don't want to go into much detail here, but there are things like exploring the immediate neighborhood of nodes, pattern matching, navigational queries, aggregation, subqueries, etc. And we also defined like examples for that, and for certain functionalities also more sort of formal definitions what we mean by that. And this catalog is more a reference which we can use to see if certain proposals or to discuss certain proposals and find out their limitations and strong points. Okay, what we also have accomplished is formal definition of this is a starting point. We are not sure yet if that will be the final form of the data model, but you have to start somewhere. So we have a formal definition of the property graph model. And another thing we did more recently is that we enriched that with a tabular view of graphs. So, so that we can also see how this very formal and abstract graph data model can be represented in tables. And that kind of completes the picture a bit to not just fly around on this very formal abstraction, but get also a feeling how it could be implemented in systems and what consequences are attached to certain decisions you do on this very abstract formal model. And it also helps to better understand, see the differences to SQL. So what we actually get as additional things when we look at graphs, and so where are commonalities and where are differences. And yeah, it also helps to understand how a graph query language could be integrated with what we have for tables, because that is also something which will definitely be necessary for a proposal to be successful. Okay, so how could that look like? Yeah, basically we extended the definition of this graph query model by certain built-in properties that then allow us to define tables which represent the graphs we can describe in the query model. And here's an example which makes it, I guess, more clear than these formulas. So if that is our graph without properties here for simplicity, so it's some green nodes and some yellow nodes and blue edges in between, then we think of that as either two tables or V and E or a nested variant of that. So blue are the nodes with their ID and their label. And the orange part are the outgoing edges of each node with their also an ID and their destination or their target. So you can think of that also as a sort of an adjacency. And the query then could look like you specify a match pattern that would run on this table, and if you project to the variables in the pattern, what you basically get is new nodes. So you again would get a graph consisting of, in that case, as many nodes as you have matches, and each match is basically represented as a node. So that was some initial idea. What you get by that is that you introduce explicitly the identities of objects. In this very abstract definition of the data model, you don't see that. We just say there are nodes, there are edges. But here it becomes more clear that you somehow need to manage identities. And there are also certain questions attached to that, which we discussed. And so some decisions we did is regarding the immutability of objects. So if we have an object with an ID, can we change basically the object but keeping the ID? Or within a query, and we say, no, we don't want that, because that would be DML, and in DML operation. And currently we're just looking at DQL operation, so pure querying. And queries should not change the object. Oh, sorry, this slide. But there are cases where you kind of need that. For example, when you want to throw away certain properties because you are just interested in some parts of the object, then we basically say, okay, the query language should just create a new transient object. And the consequence is then that basically within the scope of the query, you can say that the identity functionally determines the object is made of. And if you want to, within a query, create new objects, then of course you must be able to create new identities. And that's also something we discussed, how you organize identity generation. And particular, what is the scope of this generation? Because the identities need to be unique, as we know. Should they be unique for all times the whole system runs? Or so what is the scope of this uniqueness? And this is basically a trade-off between how complicated is it to implement and how broad are the guarantees you get. And we thought that limiting the uniqueness to the scope of a transaction or a single query is a good compromise. And that also, the other question is how the repeatability regarding the ID generation. So if you run the same query twice, do you get the same ID? And as we see these IDs more as a system internal identifier, we think you don't need to have repeatability in ID generation. So there's no need to make a system guarantee that because you need a lot of additional bookkeeping to guarantee to produce always the same IDs. Okay, so what are current discussion points? One discussion which is currently heavily going on is how you can represent represent paths. As I said in the Dresden, and the data model definition I showed is there are no paths at all. So the question is how do we bring paths into the picture? And there are certain points how you can do that. So one is you try to use the existing elements in the data model to somehow represent paths. There are ways how you could do that, but the nice thing is that it keeps the data model simple. But the not so nice thing is that then paths are not really a first-class citizen, and you add a lot of interpretation on top by defining how you actually represent paths. And that basically makes things more complicated for whoever who will be the user of that language. Another thing we discussed is that you could represent paths in just as property values. So you would introduce a new type like path. So you could have properties which contain a path. But that would introduce non-atomic types to your data model, which complicates the language. And another thing that comes up in this discussion is, do you want to actually represent these paths by their elements? So really the nodes and edges the path is made of, or just by referencing the IDs in the original graph. So people also have different expectations regarding that question. And one current favorite, but not yet decided in the discussion, is to have to use the idea of logical paths. And that is similar to what we heard yesterday for the ones who attended also the OpenCypher meeting, with the logical graphs in the Hadoop data model. Similar idea, you have your graph. You would run, and additionally to that graph, to the elements of the graph, nodes and edges, you have paths, and in the base data, you don't have logical paths. So logical paths are basically just a way to mark out certain paths in the graph. And in your base data, you don't mark out any paths. And when you run a query and select certain paths, then you would get the part of the graph that contains your paths and additionally mark out these paths. So for instance, this path is additionally marked out. But by that you kind of accomplish both, so to say. You represent the paths by reference, but you also have all the elements that make up the path. And we now have to see if we just want to go that way, or if you also want to have logical graphs. Do we need both, or can we kind of combine them into one concept? These are questions we need to discuss. Another discussion point is projection. So if you want to produce new elements, new nodes, new edges, how powerful do we make the projection? One approach is to make it more like in relational query languages, so that with one projection you just can project to one type of thing, so to one type of nodes and one type of relations or edges. And if you want to produce more complex graphs consisting of different node types and different edge types, you could use union. So this kind of things, this kind of keeps concepts orthogonal, which is nice. But it's somewhat unclear if you want to produce an edge which links different node types, how you do that. And another idea is to have a graph transformation-like projection. Here you essentially describe what you project as a subgraph pattern. This is more intuitive and more graphy, but on the downside, it's not 100% orthogonal to union. So to explain the later point a little bit by example, again, we have this graph here. And if we now run a query which looks for the shortest paths between green nodes and blue nodes, we could project these matches to subgraphs consisting of the green node X and the blue nodes Y, and produce a new edge, for instance, between those, which just gives us the length of the path, for instance. Or you could also go further and enrich that with aggregation by saying, okay, on the blue side, I want to not have the individual blue nodes, but group them according to the X side, and then we just get one blue node instead of two. And then you could aggregate, for instance, all the paths and find out the average length of the path. Okay, and by that I would sum up the talk. So what we have accomplished so far is a catalog of functionalities, a core data model, and we look to the principles of object identities. Current discussion points are data model extensions towards path representation and principles of graph construction. And there are still a lot of work ahead of us. So now we have sort of different pieces we at some point need to put together to get semantics or defined semantics for core of the language. And from there we kind of have to go on to extend that to more advanced concepts. And at some point we also sort of have to nail down some syntax. Yeah, by that I'm done and I'm open for questions. Yeah, Mats?
So you mentioned that you'd like to keep the objects immutable,
Mm-hmm.
and that you wanted that in order to keep the language separate from the data that you give it. Why is that decided?
So in terms of orthogonality, it's desirable. So it just, if you mix DML with DQL, concept-wise, you would get multiple language constructs which can accomplish similar things, and this is not orthogonal. It's like you would have headlights on your windswipers at the car. So it doesn't really make sense when it's dark. Do you switch on the windswipers or the headlights? And these kind of confusions you typically want to avoid in a language in general, not just query languages, but also programming languages. So this is, orthogonality is just a good design principle for languages. And we want to keep to that, because it makes also, when you mix concepts, it becomes hard for the query writer to reason about the consequences of something. And when someone, a person wants to write a query, the intention is not to change the base data, right? And if that person always has to think about, oh, has this query side effects to the base data, it's, we think it's not a good thing to have. So there should be a clear separation between querying data and manipulating data.
Right, but that poses the question, when do we get allowed to do the manipulation of the data? I mean, you're effectively saying you must build a system that's based on that immutability of data. That's extremely restrictive from an implementation perspective.
No. You got me wrong. I don't. Are separate. You have concepts for manipulating the data, and you have concepts for querying the data.
Okay, so I guess that was my question. At what point in this process it's like giving up meat for Lent or alcohol in January? Come February, I want to drink. Yeah, when do I get to drink the LDBC query language?
So we think the more complicated part is the query part. That's why we focus on that. But of course, at some point, we also need to talk about manipulation. But when you look at Cypher, the manipulation part borrows a lot from the query part.
Sure,
yeah. So.
About the limitation here, the scope issue. Like, when is that scope going to be relaxed to take into account the manipulation stuff?
So there's not a point in time fixed, but I could describe the point in time by saying we do that once we have a good standing of the query.
Also maybe one point, if I may. It's nice to say we want to keep DQL and DML separate, right? But if you are really consequential about that and treat them as separate language, it means essentially that you introduce a client-server request cycle whenever you want to do an update based on what you have written. Because if you in your query can send a mix of DQL and DML, right? Then if there's one request going to the server, you do a query based on your query results, you perform an update. Right?
But I haven't said that it's two languages.
Ah, okay.
You said that. I didn't say. I just said we have.
It sounded very much like that.
I just said we have different concepts for that. We don't have concepts that are primarily meant for querying, but also change data. I want to have concepts that are meant for querying and concepts that are meant for updating the data. Yeah. But of course, that doesn't say that you can send one request to the server which can do both, where you call both concepts.
So you showed some expressions involving paths, and I was wondering how expressively constraints can make on the nodes of edges which compose the path. So you have one example where you said, okay, there's a friend plus, so only edges of type friend.
Yeah.
So can you make this some more elaborate constraints on the path?
So we haven't dived into details here, but the power we assume there are the ones that you have in regular path queries. So this is a concept which is clearly described in the literature. So you basically describe the path by a regular expression over its labels, and that is so currently what we are aiming at. But the question we are currently looking at are, I would say, more fundamental, how we...
There was actually a long discussion, but I think that we kind of reached an agreement on roughly the functionality in that area.
Yeah.
Because there was, regular path queries are well understood, but then people also want to do selections on them.
Yeah.
But I think we reached an agreement that's kind of balanced in terms of complexity and functionality,
Yeah.
expressivity.
More questions? By that, there's one last question, yeah.
The core data model, I saw that you introduced a specific set for modeling graphs or for sorting graphs. Is that correct?
Yes.
Like for example in our data model. And I was wondering if the
No, here is it. Here, these are not. Where is
so
it?
the G there is a unit set of graphs
Mm,
on that side.
yeah, here. So that is not meant as logical graphs. It's just to have that a database can consist of multiple graphs.
But it's not like they can overlap or something.
No,
like this.
not yet. Yeah.
Okay. Considering the operators that you introduced at the end that use aggregation to create new vertices, for example, and then those new vertices are again connected to the original ones, did you also consider like the hypervertex model in that case because it's similar to that?
Not yet. No.
There should be an invitation to join the task force.
Yeah. You're welcome to do. I just, like last week, sent around your paper on logical subgraphs. So maybe you will want to present that to the language task force. Okay, by that, I will close and give it to the next speaker. Thanks.